Okay, so we continue with exercise 11. Now here we are given this function f of x, which is a rational function, a ratio of two polynomials. The numerator is x squared minus 9 and the denominator is x plus 3. And you can immediately see that this function is defined for all real numbers x except x equal to minus 3, because for that value the denominator becomes 0. Now naturally we would investigate about this limit, that is what happens to the f values as x approaches minus 3, that problematic point. Now there are three parts. In the first part we investigate things numerically. So some points, that is some input values are given which are near minus 3. These values minus 3.1, minus 3.01, minus 3.001, and the number of zeros increases. So precisely this is being asked here. Make a table of values of f at these points, and of course you have to follow this pattern by increasing the number of zeros and so on as far as your calculator can go, because after a certain extent you will run out of space in your calculator. And then from that table of the corresponding y values or f of x values, you have to estimate the value of this limit. Now you can see that all these points x values are less than minus 3. But as you go down this sequence, you get closer and closer to minus 3. So they increase, but still none of them is equal to minus 3. In fact, at x equal to minus 3, of course, this is undefined. So you see those values, and then from those values you estimate this limit. On the other hand, if you choose values again close to minus 3, but all of which are greater than minus 3, that is these values, then also you can estimate that same limit. So what estimate do you get when you use these values instead? That is, for these values also you make a table of the corresponding f of x values, and then you estimate this. So this part I am leaving to you, obviously, because you are supposed to make those tables and see what happens. And then in part B, you are to use some graphing calculator. So using that, you graph the function f near x equal to minus 3, and then you use the zoom and trace tools in your grapher to estimate the y values on the graph as x tends to minus 3. That is, as you choose your x values closer and closer to minus 3, again you see what happens to the corresponding y values. But now instead of doing things numerically, you do it on a graph, a graphing facility. So that also you do, you see what happens. Instead, what we are going to do is this part C. We will solve part C. Find this limit algebraically. Okay, so let's see that. So let me keep the function and let me start the solution from here. And one more thing, just like for those values of x near minus 3, but where all the x are less than minus 3, you have to go as far as you can, or as far as your calculator allows. Here also you have to do that. Now we can recall that the value of this limit depends on the fx values. The f values, of course, they only determine what the limit is going to be, but only near the point minus 3. the limit actually has nothing to do with what goes on at minus 3. In fact, here nothing goes on at minus 3. The function is, the way it has been given, it is undefined at minus 3. But that has nothing to do with this limiting value. And that's why when you see this limit and when you see this symbol, it means that x is close to minus 3 but not equal to minus 3. So you can write, since x is not equal to minus 3, we have x plus 3 not equal to 0, and so f of x, which is this, and hence which is this, now reduces to x minus 3. That is because x plus 3 is non-zero, so you can cancel these two things and have x minus 3. So really the function is just f of x equal to x minus 3, and the domain is the set of all real numbers except minus 3. Hence, so what would this limit be? Now that you have reduced the formula to this, the limit will obviously be minus 6. Keep in mind, this is one great mistake in interpreting this equation, that I put x equal to minus 3 here in the formula and I get the limit. That's not how we should interpret it. We should interpret it in this way. As you make x closer and closer to minus 3, the corresponding x minus 3 values get closer and closer to minus 6, and that is why the limit is minus 6. Yes, it is also true that if you really put x equal to minus 3 here in this expression, then you do get the limiting value. But that's not how we are getting the limiting value. The limiting value is minus 6. And it happens to also be true that if we put x equal to minus 3, then we get the limiting value. And based on that, we will see the next set of exercises, that you can in fact put x equal to minus 3. So whatever value you get, that happens to be the limiting value also. Okay, so that's how, using algebra, we can actually see our use of algebra has allowed us to do what here? It has just allowed us to simplify the formula of the function and hence to have a better guess at what the limiting value actually will be. So that's how we get this. But again, let me repeat, keep in mind, x is, you are not putting x equal to minus 3 here to get the limit. That is not the limiting process. The limiting process, this symbol means it is that value towards which the f of x values are approaching as x is approaching minus 3, but it has nothing to do with x being equal to minus 3 because x is not minus 3. See? But in order to guess what the value of the limit is, we do get minus 6 when we take x equal to minus 3, but that is just for you to guess at the limiting value. That is actually not what is going on in this limiting process. X is not equal to minus 3. Okay. So that interpretation should be clear. Now after this, some such, in fact many of the exercises after this 11th one are like this. So those things I leave to you. In anyway, here also you have to solve parts A and B on your own. So you please go through those things, and if you find any difficulty or if you find any confusion, please let me know. And now what we are going to do is this. We are now going to solve exercises 21 through 28 by precisely following this thing. That is, we are here going to look at those exercises where we do get the limit if we just substitute this value. Just like here, if you take x equal to -3, you get -6, and that happens to also be the limiting value. So let's see this next set of exercises. Here, taking x equal to -3 in the formula for the function gives you the limit, but that is not always the case. The functions in which that is the case, they are called continuous functions. We will see more about this later on. So this one has the heading limits by substitution. And under this heading we have this. In exercises 21 through 28, find the limits by substitution. Support your answers with a graphing device, a grapher or calculator. If available. So in these exercises we are just going to substitute, and that's it. So we will get some value, but that is just a mechanical process, right? You just substitute the x value and you are getting some value. What is the guarantee that what you are getting is in fact the limit? So to see that, you will have to either use some graphing calculator or an ordinary calculator. That is, either you check things geometrically or numerically. So that part will be left to you. So let's now see exercise 21. So here the limit is these are going to be extremely easy. Easy in the sense, I mean, in terms of getting the answer, it's almost trivial, but that's not the point. Here you can see that if you put x equal to 2, you will get 4. So you declare that the limit is 4, but is it really 4? Do we really get close to 4 as x gets close to 2 and when your function is 2x? To see that, you either draw the graph of this function and then see what is happening near x equal to 2, in the graph, that is what happens to the y values or 2x values, or you take a calculator and make some tables where you take x values close to 2, on this side of 2 and also on that side of 2, and then you see what happens to the 2x value. Again, I am repeating, do not take x equal to 2 in your when you are making those tables, because x is not equal to 2. When you are considering any such limit, the independent variable is not equal to this value. Always keep this in mind. So what I have to write here is almost something that need not even be written. So this is 4. That's what we get when we substitute. 2 for x. Okay. Now before we go to exercise 22, let me address one issue. You see, when we encounter limit and when we start calculating limits of functions, we do see this kind of things only. That is, we substitute this value itself in the function and we somehow convince ourselves that this is the limit. So remember, I said that this happens only when the function is continuous. The fact is that most of the functions that we come across at this level in calculus are continuous. So this method of substituting the value and getting the limit works in most of the cases, and that in fact confuses us much more. That's because on one hand we are saying that x is not equal to 2. On the other hand, we are also taking x equal to 2 and finding the limit. So this confuses the hell out of us. But again, for one last time, let me repeat it. The process of knowing what this value is does not involve taking x equal to 2. Okay. What does it involve? It involves taking values of x that are close to 2. If you take values of x that are close to 2 but that are greater than 2, then those values look like this. They look like this. And you can see that as you increase the number of zeros, this is decreasing, right? This is oh, I cannot take 2 itself, no? Yeah, I can take 2.1. So as you increase the number of zeros, these values are, let's say you have 2 here and say you have 2.1 here, then 2.01 will be a little closer to 2 than this one. Then 2.001 will be still a little closer to 2, like that. On the other hand, you can also consider values of x to the left of 2, that is the values which are less than 2. And you can increase the number of 9s after the decimal point. Then that will increase the values and you will get closer and closer to 2. So the limiting process involves finding the corresponding 2x values for these values of x and then seeing where the 2x values are heading. you will see that those values are heading towards 4, and that is why the limit is 4. But in order to avoid all of this and straight away getting the result, sometimes if we really take x equal to 2 here itself, then we will get some value. Now, if there is no problem in putting x equal to 2 in the function, then we will get some value. It turns out that this actual limiting value and this value followed from the substitution turn out to be the same, okay, in most of the cases. That's why this method of substitution works, but it is obviously not something that can always be done. If the function fails to be continuous at x equal to 2, which is something we will see, then problems can arise. Then the actual limit may not be what you get when you substitute that x value. Okay, but here in these exercises, we can substitute. And what is the guarantee that whatever we are getting by substituting is really the limiting value? That guarantee will be provided by your grapher or calculator. That's why this is not, you just write this and stop that. No, that won't give you the guarantee that this itself is the limiting value. You have to back this up with a grapher or calculator and doing whatever you are supposed to do. Okay, so that's the point. But anyway, let's just see the next one. Here the function is same, but the independent variable is approaching 0. Just simple substitution gives us this value, which once you use grapher or calculator, you will see that that's what the actual limit also is. So if you just simply substitute x equal to 1 over 3, you get 0. Now do you notice one thing, that in our 11th exercise we had this function. Now here also one can get the limit as x approaching -3 by substitution, and in fact that's what we did there. But you cannot immediately put x equal to -3 in the formula of the function itself. You have to simplify it, reduce it as much as possible so that we can see what the final expression is. So it is often the case that even when substitution is allowed and you can hence substitute, it may not be immediate. It may be somewhat like this. You may have to do some things to the function formula in order to make it, in order to take it in a form in which you can substitute. Here you cannot substitute x equal to -3. Okay. Next, 24. Limit x is approaching 1 minus 1 over 3x minus 1. We have, you can write we have always. So that means all these solutions are incomplete. They will be complete only when you justify them with a grapher or a calculator. Yeah, I think none of this is going to be like this. Three x times 2x minus 1 as x is approaching minus 1. Okay, so minus 2 minus 1 is minus 3. Minus 3 times minus 1 is 3, and 3 times 3 is 9. Three x square over 2x minus 1. So in the numerator we have 3, in the denominator we have minus 3, so minus 1. X is approaching pi over 2, and the function is x sine x. So here the limit is pi over 2. And the last one is 28. Here x is approaching pi, and the function is what? Cos x over 1 minus pi. Oh, so the denominator actually is a constant. Fine. Cos pi over 1 minus pi. Cos pi radian is -1. So that means -1 over 1 minus pi, which is 1 over pi minus 1. Okay. The next set of exercises is about calculating average rates of change for some functions over some given intervals. Average rates of change. I think I need ink. I forgot to refill it beforehand. In exercises 29 through 34, find the average rate of change. Of the function over the given interval. Or intervals. So here the function is x cube plus 1, and there are two intervals given. In part A, the interval is the closed interval 2, 3, and in part B it's the closed interval -1, 1. The average, I'm forgetting spellings also. The average rate of change of f in the interval 2, 3 is, we already know what average rate is, f of 3 minus f of 2 divided by 3 minus 2. and you can calculate it, and the value will be 19. Similarly, in part B, there is no need to keep on writing the same thing, because that's what it's going to be. Just in place of this interval, you are going to write this interval now, and the value is going to be f of 1 minus f of minus 1 divided by 1 minus minus 1. That means you have 2 in the denominator, and here the value, I think it is 1. Yes. Here the function is the square function, and the intervals are these. Minus 1 comma 1 and minus 2 comma 0. So in part A, it's just this quotient so you can see that here you will have the square of 1, which is 1, minus you will have the square of minus 1, and the square of minus 1 is again 1, so 1 minus 1 is going to give you 0. So here the average rate, there is no average rate of change, and in other words, that rate of change is 0. On average, there is no change in this interval. But when you consider it's symmetric about the real number x equal to 0, that one is not. So there we are going to see some rate of change. G of 0 minus G of minus 2. Always when you calculate this average rate of change, you take this minus this. And even if you take the opposite order, you have to maintain that order in the denominator also, but that is a little unnatural. We always take the final point minus the initial point. If you are following the this direction in which the x values are increasing, that is, as x increases from minus 2 to 0, what happens to the g values? So the length of the interval also, which comes in the denominator, is calculated in that way: final endpoint minus initial endpoint. 0 minus minus 2. So this is going to be what, since it's a square function, it's easy to calculate. You have this one, of course, will be 0. This one will be g of minus 2 is the square of minus 2, 4. So minus 4 in the numerator and 2 in the denominator. So that means minus 2. Yeah, of course, it's minus 2. This one has the cotangent function, cot t, and the intervals also are somewhat like that. I mean, they involve pi and ratios of pi. Fractions of pi: pi over 4 comma 3 pi over 4, and b is pi over 6 comma pi over 2. and here the final answer is minus 4 over 5. You can of course put these values in the function and see if that is the case. And in part B, here the final answer is minus 3 root 3 over pi. Next, $32. Yes. In 32, the function is g of t equal to 2 plus cos t, ordinary cosine function. And here also two intervals are given, closed intervals 0, pi and closed interval minus pi, pi. Over the first interval, the average rate of change is g of pi minus g of 0 over pi minus 0. So 2 plus cos pi minus 2 minus cos 0. So that 2 and this 2, they cancel out. Cos pi minus cos 0. Cos pi is minus 1, minus cos 0 is 1. So you get minus 2 in the numerator, and pi is of course there in the denominator. So the average rate of change should be this minus 2 over pi. Yes. In part B, the interval is this. Now here we have pi and minus pi. Okay. Now let us see for a moment what is the value of g of pi. G of pi is 2 plus cos pi. What that ultimately turns out to be, there is no need to know that. What is g of minus pi? G of minus pi is also 2 plus cos minus pi, but cos minus pi is the same as cos pi. So these two values are the same. So you get 0 in the numerator, and so the average rate of change is 0. There is no rate of change. And also you do one more thing in this set of exercises. You draw the graphs of these functions and look at what is happening over the indicated intervals in the graph, and then you try to think of what can you make of these average rates of change values, and what do these values say about the graph in that interval? You please do that. Have I? Oh, this is 33. How can it be 34? So in 33, the function is r of theta and the function definition is this: square root of 4 theta plus 1, and here only one interval is given, 0, 2. Calculus is a very visual thing. I mean, at least at this level where we have only one independent variable, we can draw graphs very easily. We also have graphing calculator. I mean, the online facility is there, that Desmos graphing calculator. You type this in whatever browser you are using, maybe say Chrome. You will get the first result itself will give you this, and there you can very nicely draw graphs of any kind of functions. So the thing is that in order to see what a function is doing and how the values of the function are behaving, it's almost always not just useful, but in fact it should be essential to draw the graph and see what is going on visually. It is an advice that is given by the authors, and it is also in general true in mathematics, not just calculus. Whenever you want to understand something properly and there is a scope of drawing some sort of diagram, we should draw it just for our own sake in order to better understand what's going on. So that's why I'm also asking you to take the help of this graphing facility and see what is going on with these functions, because if we just simply look at the formula, it's an abstract formula. We cannot immediately see what the formula is going to give us, what sort of values it will give us for each input value, and how do the values look together. That is the graph. No, so we have to draw graphs as many times as we can. Okay, so here the average rate of change is of course this. Okay, and this one we can of course calculate quite easily. If we put theta equal to 2, we get 9 here, whose non-negative square root is 3. Minus r of 0 is going to be 1. So 3 minus 1 gives us 2 in the numerator, and 2 is there in the denominator. So here the average rate of change is 1. And finally, the 34th one, P of theta is theta q, it's a polynomial in theta, minus 4 theta square plus 5 theta. And what is the, here also only one interval is given. Over this interval we have to calculate the average rate of change, 1, 2. And the average rate of change of course is just this, and you will you calculate, you will see that P of 1 is equal to P of 2. So that's why the average rate of change will be 0. So that's just it. Let me just end the video here itself. We are going to see the other exercises of this set of exercises in the next calculus update. And tomorrow, let us go back to Galilean's group theory problems. After that, in the next on next Saturday. Tomorrow is Saturday. The one after that, we will again go back to Gallien's ring theory problem, and then again Lie. So it rotates like this: Gallian group, Gallian ring, Lie, group, ring, Lie. Like that it goes. So see you tomorrow with that. Until then, this is me, Lucifer, from a mathematical group. Have a nice night.